In our lesson about exponential functions, we learned about transformations of exponential functions, and we also learned about growth and decay. We started with our transformations, and we used f of x equals 2 to the x as our parent function. And then we translated that function using a and h and k. So we had a times 2 to the x minus h plus k. And after some exploration looking at graphs, we noticed that a and h and k do the same thing for exponential graphs that they did for absolute value graphs. We noticed that the value of a made it a vertical shrink or a stretch. Sometimes instead of shrink, we say compression. So I'm going to say vertical stretch or compression, depending on its value. We know that if the absolute value of a is between 0 and 1, it's going to be a compression. And if the absolute value of a is greater than 1, it's going to be a vertical stretch. We also saw that when a is negative, it was a reflection. So it could also be a reflection. Not every graph is going to have a stretch or a compression or a reflection. So we have to look and see. These reflections are going to be reflections over the x-axis. We noticed that h was a horizontal shift. It would translate our graph left or right. We also noticed that it, again, looks like it does the opposite of what we might expect it to do. So if it was x plus 2, it would move us to the left 2. And k was going to do a vertical translation up or down. Up if k is positive, and down if k is negative. So let's look at an example. In this example, we notice that our a has a value of 3. That means that this is going to be a vertical stretch by a factor of 3. We see up here we have x plus 1, so we know h is really negative 1, moving us to the left 1, and k is minus 4, so this is going to move down 4. So we have a vertical stretch, by a factor of 3. We have a translation, left 1 and down 4. Now, when we think about this graph, normally the graph of 2 to the x would be something like this, where y equals 0 is our horizontal asymptote, and we have a y-intercept of 0, 1. For this graph, we see that it's moved left 1 and down 4, and it's a vertical stretch, so it's going to look a little bit different. Although without making a table, it's kind of hard to tell exactly what it looks like, there's a few things we can do. We know that since it has been translated down 4, so has our horizontal asymptote. So the horizontal asymptote is normally at y equals 0. Our horizontal asymptote is going to be down here at y equals negative 4. Since that's our horizontal asymptote, we know everything in our graph is going to be above that. So we know that the range for our graph is going to be y is greater than negative 4. Our domain, since this is an exponential function, our domain is going to be all real numbers. Now, if we'd like to know where our y-intercept is, we always like to know where the y-intercept is, we can plug in a 0 for our x value. Let me zoom out a little bit so we can see this work. So we're going to say, to find f of 0, we're going to say 3 times 2 to the 0 plus 1. We're plugging in our 0 for the x, minus 4. So you're going to follow your order of operations. You're going to add what's in the parentheses. 0 plus 1 is 1. And then 2 to the first is just 2. So we have 3 times 2 minus 4. 3 times 2 is 6. Minus 4 is 2. So 0, 2 would be your y-intercept. We can go ahead, we know that that one was at 0, 1, so 0, 2 would be up here, and we know our graph's going to do something like that. We don't know exactly what it's doing, but we know it's growth, because our base is larger than 1, so we know it's going to be increasing as it goes. All right, those were our transformations. Then we talked about the growth and decay function, which was a little bit of a review from last year. And the equation that we learned from that was f of x equals a times either 1 plus r or 1 minus r, so sometimes we write that all together, to the power of x. A was always our initial amount, whatever our starting value was. So we looked at some examples with caffeine. That would be the amount of caffeine that the person took in, would be your initial amount. R is the rate of increase or decrease. Remember that the rate is given as a percent, and it needs to be changed from a percent into a decimal by dividing by 100. So remember to do that before you plug something in. And then what x represents changes from problem to problem. It might be the number of years, it might be the number of bounces. You've got to read each question carefully and see what you're looking for. Here's an example of the types of problems that we looked at. We have a rubber bouncy ball is dropped from a height of 130 inches onto a hard flat floor. After each bounce, the ball returns to a height that is 12% less than the previous maximum height. Write an equation to find the maximum height reached after the nth bounce. So we see the nth bounce, that tells us our variable is going to be n for the number of bounces. So we're going to say f of n equals. So we want to start with our initial amount, which is 130 inches. That was the highest bounce. And then we're going to say 1, since this is a 12% less than, that means that the height is decreasing each time. We're going to do 1 minus 12%, which is 12 hundredths, so 0.12, to the nth power, however many bounces that is. And then we're going to go ahead and simplify what's in those parentheses. 1 minus 12 hundredths would be 88 hundredths. And this would be our function. And then if we wanted to know how high it went after 1 bounce or 2 bounces or 12 bounces, we could plug that number in and get an idea of what we were working with.